Hello and welcome to our final presentation. We are here proposing the idea of Plantiful, an intelligent monitoring system for precision agriculture.
And now for the group that's behind this project idea, starting with myself, Tamer Basta, my colleagues Farah Seifeldin, Lobna ElHawary, Mariam ElZiady, and Maram Abbas, and we're supervised by Drs. Mohamed Shalan and Dr. Tamer ElBatt.
For our current presentation roadmap, there are four main sections. The first one, which is the one we're about to go into, is the idea section. We'll be talking generally about our idea. The second section is the design methodology section. This is the core part of our presentation, and this is the more technical part of our presentation. The third section is the demo section, where we'll be showing a video of our project working. And finally, our empowerment outcome, which is community deployment.
After doing our own research, we realized that a lot of time is wasted taking sensor measurements in agricultural fields and greenhouses. Moreover, this amount of data is very hard to collect manually. Also, experts are needed to diagnose crop health, but they are not always available on field. Additionally, COVID-19 has led to a decrease in present personnel on agricultural fields and greenhouses, which leads us to our proposed solution.
I'm going to start dissecting our project title now so that you can have a better understanding of what our project really does. Intelligent here signifies the machine learning and computer vision portion of our project. This is through the plant health model and the growth stage detection model. Plant health checks the healthiness of the plants, while the growth stage detection checks the stage that the plants are currently in. The monitoring system here signifies the Internet of Things portion of our project, which is the remote sensing network. These are sensor blocks consisting of three main sensors, and their main goal is to capture these sensor readings and to be stored to be showcased later to our users. And now lastly, with precision agriculture. In definition, this means the modern information technology to improve agriculture. This is exactly what we're doing, with the first two portions an intelligent monitoring system. So with a web application, we are tying them all together so that we can notify our users if anything's out of place, with all the sensor readings, the photos, and everything. And we are going to be physically deploying this at CARES as part of a community deployment. CARES is a center for applied research on the environment and sustainability, as they are the main center here in AUC that cares about agriculture. I'll be taking us through the design and results section of our presentation. And here is our system architecture. It's split into three microservices, just like our title was split into three earlier. So microservice 1 is the monitoring system with the remote sensing network, microservice 2 is the plant analyzer, our intelligent portion of our project, and finally the microservice 3 is our core application, which is the web application. Now Maram will be continuing by going into the details of our remote sensing system.
Regarding our remote sensing architecture, as you can see, we have each sensor block connected to an ESP32. The Raspberry Pi here acts as a server to all the sensor nodes and the camera as well. It receives from the sensor node the data and uploads it to the database, and it also receives images from the IP camera and uploads it to the cloud storage. We have a scalability problem that we may face, that any router used will have a limited number of connections to it. So in order to solve that problem, more routers or access points to the main router can be used, or even we can double the number of sensors that can be connected to one ESP. So what is a sensor node? A sensor node is a block consisting of an ESP32 that takes readings from three sensors, which are the DHT11, which measures temperature and humidity. Another sensor is the soil moisture sensor, and finally the pH sensor. We collectively take these four main readings after each interval that the user chooses. The picture on the left demonstrates how the sensor block is put together and how the pH and soil moisture sensors are put inside the soil. We have ordered the PCBs for the sensor nodes. However, a miscommunication happened with the company that we're ordering from, and actually it's arriving tomorrow, which is why we can't add a real picture of them. However, it's shown on the right. It is decided that a unique ID is given to each sensor node. This unique identifier is chosen to be the ESP32 MAC address. And finally, when setting a sensor node, the ESP32 will create an access point that you can connect to it in order to configure it with the settings that you think suits best with your project. More information on that part will be provided in the demo in the following slides. As you can see here, one sensor node costs about $42. It may be a really good one-time cost comparing to the recurring costs paid as salaries to the workers who are assigned to monitor the plants. Now for the system power, assuming the user chose to take readings in an interval of 10 minutes, batteries with a capacity of 2300 milliampere hour will need to be changed or recharged after 14 days. Now moving to the core app. So our web application is deployed on Heroku. We are using Django framework for the front end and back end. So with the server side, we have also deployed our plant health and growth stage detection analyzers. And finally, the database we're using is a Postgres SQL database. And here's our updated database entity relationship diagram. However, for the sake of time, I'll not be going through it. Rather, it's here for anyone that would want to know anything about it. Now, Farah and Mariam will take us through the AI portion of our project.
We will now discuss the health detection model. Because the online found images of healthy and unhealthy plants were sometimes very similar, we opted for a crop-inclusive machine learning model that classifies leaves from numerous plants into healthy and unhealthy without reporting the cause of the unhealthy nature. For each version of our model, each sub-dataset was divided into 80% for training and 20% for testing, for the sake of adequate representativeness. Our health dataset is the combination of these 4 sub-datasets. The first sub-dataset is the 173 images of cucumber leaves we manually took at CARES and labeled with health status using expert opinion. The second sub-dataset is from Kafr Sheikh University and has nearly 700 health-labeled images of cucumber leaves. The third sub-dataset is Plant Village obtained from Kaggle, which has almost 21,000 health-labeled images of tomato, potato, and pepper leaves. Finally, the fourth sub-dataset is also called Plant Village, but obtained from TensorFlow and has almost 60,000 health-labeled images of 14 plants. Here are the results of the testing of our model as it stands. 7 trials were conducted using a CNN, then an SVM with various training testing combinations. The best trial yielded a 94% accuracy and was the one using an SVM with an RBF kernel implemented on our sub-dataset, the KU sub-dataset, and Kaggle's Plant Village. The 3 yielding a total of around 21,500 images. These images were used for both training and testing with an 80-20 split for each sub-dataset as explained before. And this accuracy is a significant improvement from our previous 65% accuracy, which belonged to the VGG16 CNN. As for the deployment of our health model, segmentation was used on the camera captured images in order to match them to the training form. The segmentation method involves obtaining contours in the HSV color space. The contours desired to be found are medium-sized as informed by the agricultural experts. Also, the segmenter optimizes for the best hue sensitivity for each image. Because the highest performing and currently deployed SVM was trained and tested on images of bell pepper, cucumber, potato, and tomato, the health model is fit to be deployed on greenhouses containing these plants. Now, Farah will explain the growth stage detection model.
To classify images according to their growth stage, we use a 2-step algorithm to simplify the task into 2 binary classification. The stages we aim to predict are initial flowering and fruiting. In the first step, we train a cascade classifier using manually labeled 1,000 positive samples of cucumbers and negative images to detect the cucumber fruit in an image based on the edges of the fruit. After fine-tuning the classifier, the results were very satisfying, as all cucumbers were detected along with some noise as shown in the image in the corner, which moves us to the next slide. So now that we can detect the cucumbers, we can differentiate between fruiting and non-fruiting images. We decided to test it on our entire dataset. Our testing dataset was made up of around 34% fruiting images and 66% initial and flowering images combined. And these fruiting images are different from the ones that we used for training. Our prediction logic is based on the number of fruit features detected in the image. We observed that the false positives reported in initial and fruiting images were less than 15 in many cases, so we decided to use that as our threshold for prediction. So now for our results. We achieved 94% accuracy predicting fruiting versus non-fruiting stages, and it's clear in the images that the fruiting stage has much more detected fruit features than the flowering and initial. Since accuracy isn't a good measure in our case because most of our data set actually was made up of negative images, we use precision and recall, and our precision is around 89% and our recall is around 93%, which indicate that we are able to predict fruiting stage well. So now that we're done with fruiting, our second step is to differentiate between the initial and flowering stages by creating a feature vector that represents each stage. The features we use are the total green area, the total yellow area, and the number of yellow contours having a specific area, which indicates flowers, as well as the number of green contours and yellow contours. And then we use logistic regression to predict the probability of the image falling between the two stages. We were delighted with the results, as 95% of our testing images were accurately classified, and the top row of images shows that the leaves are larger and there are more yellow flowers in the fruiting stage, while in the initial stage the leaves are much smaller with no flowers, and these were the features that we based our classification on. After combining our two steps into one algorithm and testing it on our testing dataset, we achieved 91% accuracy in predicting the current growth stage of cucumbers. While the performance of our algorithm is quite amazing, it is important to note that most of the initial and flowering images had a white background that manually removed background noise in the image, so we expect our algorithm to perform slightly worse in the field.
And now Lubna will demo the project.
So this is group 1 and this is our group 2. And this is our camera setup, and the camera captures images that are then used in our machine learning and computer vision algorithms. So as you can see in group 1, this is the first sensor block. And this is the second sensor block of group 1. And on the other hand here, group 2, we have a sensor block as well. Now we're going to create this project. So we're going to log into our website and create a new project. We're going to enter the project's settings. So its name, start date, end date, and we're going to select the number of groups, which in this case were 2. Then we're going to enter each group's settings. So we're entering 2 sensor blocks in group 1, as we saw in the video previously. The interval size refers to the time it takes between one sensor reading and the next. And here, for example, we have maximum humidity and minimum humidity. And this is a range that is specified by the user. And if the actual sensor readings are beyond that range, then the user is notified. Now we are entering the name of the settings for this group, so we can then later select it instead of every time having to fill this form out. And we're filling out the associated camera ID for this group. And quickly, we're going through group 2's settings. Now we're entering the sensor node names for each group. So in the first group, we had 2 sensor nodes, so we're entering 2 names, and these names are the MAC addresses of the ESP32, and we're doing the same thing for group 2. Now we are connecting to the sensor node access point from the Wi-Fi networks we have available, as you can see, and we're going to enter the web server of the access point and choose the Wi-Fi that we need to connect to, which in our case is the MiFi, which is called Airbox6844, and we're entering its password. And now the ESP is no longer an access point, so we can't find it. And we're going to enter the interval time that we want the readings to be taken in. Now to deploy our intelligent component, we're using an IP camera mounted on a moving car that we have configured ourselves. The camera moves and captures images of the plants, as you can see. And this is us deploying in the greenhouse. The Raspberry Pi accesses the camera stream and captures images for every set interval, and then the camera uploads this to the cloud storage. Now that we have created this new project, let's try to visualize it in a real-life setting. In our project settings, we created 2 groups. Let's say that group 1 is the first row of plants and group 2 is the second row of plants. In group 1 settings, we created 2 sensor nodes, as we can see here, and in group 2, we created 1 sensor node, as we can see here. And these are the names associated with each sensor node. And indeed, when we go to the website, we can see that the name of the project that we have created is actually there and now selected, and that there are indeed 2 groups associated with this project. Now, since we have group 1 selected, we can see now that we have the 2 sensor nodes that we have created. And if we select the second group, we should see 1 sensor node with the naming convention that we have seen in the photo. Now let's go back to group 1 and explain our results. So now that we have selected the average, this means that the results we see are an average of the 2 sensor node readings. So these 2 sensor nodes take readings of temperature, humidity, soil moisture, and pH. We average them, and then we display the latest sensor readings here. And we also have in graphical form an overview of this data. So we have the temperature, the soil moisture, the humidity, and the pH. And we know the soil moisture is correct because we did take the soil moisture sensor out of the pot. And so as we can see, the soil moisture did go down correctly. Now, if we select 1 sensor node, then we're going to see the data associated only with that node. So now since we have F8 selected, then we're seeing the readings taken from this pot. Now, since group 1 had a camera ID associated with it, we can see the latest image that the camera took for this group. And our algorithm's output was that the growth stage of these plants are fruiting. And this is indeed correct because if we look closely, we can see the cucumbers here and the small little yellow flowers. And our algorithm also told us that the leaves are unhealthy, and we can see that this is also correct because we can see the leaves are brown and they're drooping. So the algorithm does work well. Now we can also generate a report by selecting a start date and an end date. And this report will have all of this data of the temperature, soil moisture, humidity, and pH levels in a CSV file. If we also look at the notifications, we can see that we were notified because the expected range, for example, for the moisture sensor was 70 to 100% from the settings that we have selected, but what was actually detected was 26%. And this is the sensor block name associated with this error, as we can see. When a sensor reading is out of range, we also get notifications on the email. We can also change the settings that we have already created. So we can change the ranges and all the other things that we have selected. And we can also change the project settings. We can see, of course, the settings that were already applied, and we can change them and then press here and they will change. We can also choose to share a project with a user. So here I'm going to enter an email and share it with Tamer. And so what should happen is that Tamer should receive an email, which as you can see, he just did, in order to allow him to register to our website. So I'm gonna log in. So now that we're on Tamer's account, we can see that the project that I shared with him and the groups, the corresponding groups are indeed. Mariam will now explain our project's empowerment outcome.
As intended in our proposal, we have fulfilled our empowerment outcome of community deployment, as will be explained. Concerning our motivation for deployment in our local community, we were interested in advancing the technology used on campus and in aiding greenhouses worldwide. Promptly after the finalization of our thesis, we will hand over our sensor nodes and camera to CARES along with their manuals and the manual of the website. Also, we will refer the CARES team to our source code. The value of our deployment lies in our constant consultation of expertise for every decision we made throughout our development, making our precision agricultural system expert approved. The impact of our deployment in the local community involves the future prospects we have with CARES regarding solving technological problems they face in the future. Also, our deployment paves the way for other projects to take place in campus centers by encouraging students to engage with such organizations. Now, we would like to place some feedback on our project from last presentation from CARES' Dr. Chimera, the Agricultural Senior Manager.
I think it's a very, very interesting project. It has not been done so far in so many universities here in Egypt. I give a credit to them that they managed really to do what they are doing, and we also managed to do our objective. I hope that actually this work would be published, and maybe maybe the students or a certain group of people would actually proceed with the project, and it continues at least to advance.
Also, many thanks to the Director of CARES, Dr. Seifeldin, for approving the collaboration despite initial uncertainty of our abilities. We hope that our project promotes further collaborations with CARES and other research centers on campus. As for the global community, we will publish both our growth stage and health datasets on Kaggle. We will also publicly avail our GitHub repository. Finally, we will provide documentation through a code brief on GitHub. Now we will go over some of our learning achievements. We encountered physical obstacles that were further complicated by COVID-19, with shorter working hours and restrictions in AUC, as we were required to be physically present constantly during manually taking our dataset and testing our hardware components. However, these obstacles taught us time and project management skills. We also got to apply the knowledge we learned in the past 5 years by using many overlapping technologies, resulting in the complete system presented here. Thank you for listening, and please feel free to ask any questions.